Let's take a look at some graph terminology and special types of graphs. We have the concept of adjacency or neighbors. So we say that U and V are adjacent to each other if they are connected by an edge. And then we have the concept of incident. So the edge is incident with the vertices U and V because it's connecting U and V. We talk about the endpoints, connecting U and V. Next in the definition we have the degree of a vertex. So the degree of a vertex in an undirected graph, so that means that edges have no direction. The degree of a vertex here is the number of edges incident with this vertex. So if you have a loop, that contributes twice to the degree of that vertex. And to denote the degree, you use deg of V. So if you go to a party and then you start shaking hands with people, and then you're a node and every person in that party is a node, and if you shake hands, then you draw an edge between those two vertices, then how many handshakes are there in that party? So assuming that you build a graph in that way, then we have the handshaking theorem. If you have an undirected graph, so because if you shake hands with someone else, that someone else is shaking hands with you, so there is no point of having a directed graph. It's either you shake hands or you don't shake hands, so that's an undirected graph. Then if you add all of the degrees of the vertices of that undirected graph, that is going to be equal to 2 times E. So in other words, if you shake hands with everybody in the party, right, that's the condition, you shake hands with everybody in the party, so the number of edges is equal to the addition of the degrees of all the vertices divided by 2. So we have a theorem that an undirected graph has an even number of vertices of odd degree. All right, so we have another definition here. In this time we're talking about directed graphs. So the same definitions as before apply. We have the concept of adjacency. We have adjacent. The difference here is we have adjacent from, okay, from U. That changes, so it depends the direction of the edge, and then we have the initial and the terminal because it's a directed graph. So you know the direction of the edge. That has an initial point and a terminal or endpoint. The next definition we have is the in degree of a vertex and the out degree of a vertex. As you can imagine, the out degree is the number of edges that are leaving from that vertex, and the in degree is the number of edges that are arriving at that vertex. And we have these two notation for the in degree and the out degree. Always for the in degree you use the negative sign, always for the out degree you use the positive sign. We have another theorem here. So you have a graph with directed edges, so it's a digraph, okay? Then you have that some relation between the in degree and the out degree and the number of edges in the graph. You have the sum of all the in degrees is equal to the sum of all the out degrees, and that's equal to the number of edges in the graph. So let's take a look at some special simple graphs. we have complete graphs. So a complete graph is a graph where every vertex is connected to every other vertex in the graph. You use the notation k sub n, so that n is the number of vertices in the graph. And then you have cycles. So cycle C of n, that means that you have n vertices, and then you have a cycle that connects those three vertices. You have a wheel, so a wheel is a cycle with an additional vertex x connected to each of the n vertices. So if you think about the wheel, think about a bicycle wheel, where you have the center, and then you have all the spokes coming out of the center of the wheel, and that's the additional vertex x, which is connected to each of the n vertices of the cycle. Then we have bipartite graphs. A bipartite graph is such that if you remove some edges, then you're going to have two different graphs in such a way that there is no vertex that is left alone. Okay? We have a theorem here. A simple graph is bipartite if and only if it is possible to assign one of two different colors to each vertex. So if you start coloring the vertices of the graph, okay, and then you start navigating the graph, following the edges of the graph, and then you color one. You use red and yellow, so red and then yellow, and then you continue alternating the colors. So if you manage to do that, so that every vertex is not a neighbor of another vertex of the same color, then you have a bipartite graph. Then we have complete bipartite graphs. So, and then you have m and n. So one graph is going to have m vertices, the other one is going to have n vertices. Then we have the concept of a subgraph. As you can imagine, a subgraph is what you obtain by removing some edges or some vertices with all the associated edges from one graph. Then you obtain a subgraph. And then we have a proper subgraph if the two graphs are different. So note here, remember this notation is a subset, right? So remember that every set is a subset of itself. So here we are, strictly speaking, if you don't remove anything from a graph, no edges or no vertices, then the graph is a subgraph of itself according to this definition. So, but if you do remove some vertices or edges, then you have a proper subgraph, because then the graphs are different. Here is an interesting property that if you have the complete graph of three vertices as the subset or the subgraph of a graph G, then your graph is not bipartite.